All right, we're going to look at example 6.1, and we'll talk a little bit about that discussion and that diagram up above as we go through. So what we want to do is we want to answer this question. You push your physics book 1.5 meters along a horizontal tabletop with a horizontal push of 2.4 newtons, while the opposing force of friction is 0.6 newtons. How much work is done by each of the following forces on the book? Your 2.4 Newton push, the frictional force, the normal force, gravity, and what is the net work done. So we are trying to find the work done by each one of these forces and then the total work done by each of these. And so remember, work is a transfer of energy. So we want to know how much energy is each of these forces transferring to my object's kinetic energy. So in order to find work, we are going to need to use the scalar product or the dot product. Scalar product is a nice name because it means we're getting a scalar out. Even though we're putting in two vectors, we're getting out a scalar. Dot product comes from the fact that we just make a big dot to tell us that it's not just a regular old multiplication, it's a dot multiplication. What that dot really means for us is it means that I need to be multiplying the parallel component of the force times the displacement. Or I could be doing the parallel of the displacement times the force. Either way, the idea is this way is a little easier because we're better at finding components of forces. All right, so let's go ahead and give that a shot. So we'll see that all of our forces are perpendicular or parallel with that displacement of 1.5 meters. And when I go ahead to do this, I look at my input energy, and that's just typically given by an applied force. That's going to be force dot S, where the force is a positive 2.4 newtons because it's moving in the positive direction, and a positive 1.5 meters. And that will give me a positive 3.6 joules. Now, what if I had said, no, this way's negative? All right, so if I did that, I would have a negative 2.4 times a negative 1.5. I would still get a positive 3.6 joules. So whenever the force and the displacement are in the same direction, we're adding energy. Just the same way as like when velocity and acceleration are in the same direction, I'm speeding up. Same kind of concept here. Now friction, we do our dot product there. Again, they're parallel. I don't need to find the components, but I do notice that friction is pointing in the opposite direction of the displacement. So I have a negative 0.6 times 1.5 gives me a negative 0.9 joules, meaning it's removing energy. So part of the forces are trying to speed it up, part of the forces are trying to slow it down. Normal force and gravity, you'll see, are perpendicular to the displacement, meaning they are providing no energy. You need to find the parallel component to find out how much energy is being transferred. And since there is no parallel component because they're perpendicular, they are not transferring any energy whatsoever. So whenever you take the dot product of two things that are perpendicular, you get zero. And I'm just going to put my little side statement here. Because the normal force is perpendicular to displacement, because mg is perpendicular to the displacement, just to make that clear. To find the network, the overall impact of all of these forces, I need to add up all their individual works. I end up with a positive 2.7 joules. Again, this is a scalar product, so we do have a positive sign here, but it doesn't mean right or left. It simply means that we're adding energy, meaning we're speeding that object up.